Tell us something about your PhD thesis.
My PhD thesis was on Diophantine approximation.
Okay. And this is one of the major loves of your mathematical life.
With my husband, we were in Poland in 56 September or so. The year is important. And I met Steinhaus, and Steinhaus mentioned a conjecture about the fractional part of an alpha sequences where alpha is an irrational. The distribution of this sequence in 0, 1. And I proved his conjecture while being in Poland.
And this is what is called the three-distance theorem.
This is what is called the three-distance theorem, and I became so much interested in it that I realized that this so-called three-distance theorem gives a possibility to give, in some sense, a new way how to start in the Diophantine approximation, how to define continued fractions, which is, of course, a basic tool in the Diophantine approximation. And I reproved a few theorems on that way, and I proved some new theorems, and this was really the subject of my thesis.
One of the results, maybe in the thesis, you discovered a new the lovely extremal property of the golden ratio. Can you say something about that?
Yes, because one important property of this N-alpha sequence is that it is uniformly distributed in 0, 1. By the way, the first time I heard from Rényi about this fractional part N-alpha sequences, where he gave as a problem that this sequence is everywhere uniform, everywhere dense.
And Rényi asked you this question still while you were in high school?
Yes, yes. He did not ask the question to prove the question that how could I prove that it is uniformly distribution. I think it was just everywhere dense, if I want to be honest.
Okay.
But yes, and with a French colleague of mine, with Dupin, we proved that actually this N-alpha sequence belonging to the golden ratio is the best one in the sense that uniformly distributed sequence cannot be very, very good. It has a limit how well distributed it can be. It is a theorem of Wolfgang Schmidt. And we proved that that sequence is the best one. From the point of view of uniform distribution,
so the fractional parts of the multiples of the golden ratio are somehow the most uniformly, as uniformly distributed as it gets.
As it can be.
Mm-hmm. This theorem had a huge career even outside number theory. I first saw it actually mentioned in Donald Knuth's book, The Art of Programming.
Yes, but maybe the relation of N-alpha sequences to other field is more present now because it is very much related to dynamical systems and to ergodic theory. So this means that what one can see some special properties on the fractional part N-alpha sequences, quite a lot of properties hold for the orbits of a point in an ergodic transformation. So this is one thing, and really in dynamical systems itself, the Diophantine approximation, the fractional part N-alpha sequence, plays a very, very important role. A very recent result, which is due to Alan Linderstrauss, who received the Fields Prize 2 years ago. And one of the reasons was that he had some very important results in a conjecture of Littlewood about some properties of simultaneous Diophantine approximation. The conjecture says that if you consider simultaneous approximation, which means that, for example, you have two irrationals, then the whole Diophantine approximation problem becomes much, much more difficult. And one can't say that anybody can see the whole picture in simultaneous approximation. But the Littlewood conjecture formulates in a precise form that if you take a pair of irrational numbers, this pair cannot behave too badly from that point of view. And at present the world is, I think, quite far from having the proof, but Lindenstrauss proved that it is, if there are bad pairs at all, then it must be a very small set. By the way, that problem you can find on Gauer's blog, if everybody knows about it, and he formulates again and writes about the present situation of the Littlewood conjecture among the problems he used to mention on this polymath project.